One of the cases that we can use the law of sines to solve the triangle is the side-side angle case. And this is called the ambiguous case because there are actually multiple possibilities in the types of triangles that come out. So let me just draw a little picture here. We're going to, this is going to be the side that we don't know, okay? But we know an angle, and we know two sides. So this angle right here we know, and we know this side here, and then another side. Now this side over here, I don't know which direction it's. I don't know which direction it's going. I would only know its length. So you can think that this side here, if I think about its length, okay, that could kind of sweep out in all these different points. Now the way I've drawn it here, it doesn't connect at all. And so it doesn't connect down to what should be the third side. So I wouldn't get any triangle here, okay? So this is a case where if this side length right here is too short, then I don't get any triangles, okay? Now, as far as labeling, it doesn't really matter how we label, but I'm going to go and just call this angle that we know A, which makes this side length over here A. And then this other side length, I'm just going to call that B. So note that we have a condition here that A needs to be at least long enough to touch this side, okay? And so that kind of depends on this angle A, and of course this side length B. If the angle A is acute, okay, in other words, if A is less than 90 degrees, then we need this side length A, let me just get rid of that, the shortest it could be is coming straight down to touch. And if it comes straight down, then I actually have a right angle here, and I would need that side length A. I could use just the sine function, and sine of this angle A equals A over B. In other words, I would need A to be at least equal to B times the sine of A. And if that's the case, I would get one triangle. So if my angle A is acute and A is equal to B sine of A, that means I get precisely one triangle. One triangle. If it is less than that, let me move this down. If A is less than that, then it's too short. It's too short and it doesn't actually hit that line. It doesn't create a triangle, so that means you have no triangle. Okay. However, if A is greater than that, okay, A is greater than, I don't know why I wrote it all the way over there. A is greater than B sine of A. Then it's longer than this. I'm going to go ahead and erase this so that I can draw something longer and rotate it around. Okay. If it's longer, then note we don't actually know the angle C, the one up at top, which way it's going. It could be over here, could it connect like that, or it could sweep down over here and look like that. Okay, these two different lengths. I'm going to go ahead and draw those. Okay, this length A on either side, it could be either one. So I get two possible angles that it connects down here. Okay. And so we get two triangles, okay? So this will be two triangles. Okay. Now that is actually I made an assumption here. Because if A, in order to get this one over to the left, A cannot be bigger than B. If it's bigger than B, it can't connect down here. It would have to like flip around and go all the way over here, which doesn't make sense. Okay, so for that two triangles, A also has to be less than B. Now, those are the three things that can happen if this angle A that you know is an acute angle. All right? But what if A is obtuse? Or what if it's a right angle? So I'm going to look at that. If A is greater than 90 degrees, let's talk about what happens. I'm going to draw a similar picture here. I have this side length that don't actually know where it would connect, but it's got to connect along this horizontal somehow. But the angle A that's given, it's not acute, it's obtuse. Okay, so I'm going to go ahead and just draw an obtuse here. This is our angle A. And the side length over here, the other side length, side A, that I know, it can't be too short. It's got to be able to come down here. Notice that it has to be at least as long as this other side. Okay, it's going to have to go a little bit past it to connect here. So it's got to be at least that. Okay, so this side B and this side A, we need A to be at least the length of B. If it's not, if A is less than B, okay, and technically even if it's equal, it wouldn't actually create a triangle, would it? So if A is less than or equal to B, then you get no triangle. No triangle. And if A is greater than B, then there's only going to be one way that it connects. So then you'll get one triangle. Okay. Now this is actually true even if the angle A is a right angle, okay, then A is going to have to be at least B, and it's got to be a little bit past it in order to get that triangle. So this is actually if A is greater than or equal to 90 degrees. Okay, oh, there's actually one more case here that I didn't address, and that's what if A is greater than B up here. Okay, if A is greater than B. Notice then if A is greater than B, it can't connect to the left, okay, because it's got to be longer than B, and so it can only connect to the right. And in that case, then we just get one triangle again. So hopefully you can see now why this is called the ambiguous case. There are, look, these 6 different possible things that can happen, types of results that can come from knowing 2 adjacent sides and an angle opposite one of those.